Okay. I think everyone was in my previous session. We have one new person. So my name is Brandon Enright, and this is, I think the title is something like Network Security Warrior Bootcamp for the coming Malware Apocalypse or something ridiculous. The basic idea behind this PDS session, this PDS session is unlike any PDS session I've given previously, is that everyone is facing essentially a similar network security issue, whether you're a company or a school, a big school, small school, everyone's facing essentially the same issues, and everyone has a network. And I'm sure everyone's network is different, but everyone has a network, and there are some sort of similar ideas and concepts and products and tools that anyone can use on their network to help them get a handle on the malware problem. And so I'm coming from this. I've worked for UCSD for 8 years, and now I work for Cisco. I'm an information security investigator for Cisco. I do network security investigations. I look at network data, logs, and well, it's hard to summarize all the stuff I do, but basically anything that happens on the network, malware or hacking or policy-wise, is something that myself or someone in my group will look at. Cisco has a big budget, obviously, and can buy products and put together, really fancy, really world-class network security architecture and network security team, and with a whole bunch of people in a whole bunch of different sort of specialized roles to help get a handle on network security. Now, I came from a university environment, and I understand that you guys can't do that. So I want to talk about all of the data sources on your network that you may be tapping into, could be tapping into, or if they don't exist right now, data sources that you probably want to tap into. And I'll sort of talk about, what are you going to get the biggest bang for your buck? And I'm coming at this from a leverage what you already have perspective, or shoestring budget. And I also understand that everyone's network is set up completely differently. But hopefully all of them are sort of architected in sort of a similar idea. So I'm going to draw a diagram of, sort of the prototypical network, and we'll talk about the different data sources and the different data sources we already have and the ones you could possibly install. This session, again, is for you guys. So if you have any questions, or if you want to say, well, my network's not like that, my network's like this, or whatever, go ahead and interrupt me, and we can talk about it. Not everyone is going to get every data source. So the data sources that you're able to get are sort of dependent on the design of your network, the budget, the amount of resources you have, time-wise, and the people, and the amount of access you have. Some people in the room run their network. Some people in the room just run their Resnet program, and someone else runs their network. So some schools have a network security program that's relatively well developed and relatively well advanced, and so this session maybe will help you understand what they do. Maybe it'll help you influence what you can get them to do. Maybe it will allow you to convince them to do something else, or say, well, so-and-so, Brandon said you could do this, and are we doing this, and yes or no, and that's what we do. So, draw out. So, this is the internet. Most schools have access to sort of the commodity internet, and they also have access to some regional educational networks. So in California, there's the Digital California Initiative. So if you can imagine California here, and whatever the shape of California is, and, there's LA and San Diego and Stanford and Berkeley and Santa Barbara, and there's some high bandwidth network going through California called Digital California. Essentially all of the K through 12 schools, so kindergartens and elementary schools and high schools and community colleges and universities are all connected to this network. And this network, I think it's it's like a 10 gigabit backbone, but most of the schools are only connected at like 1 gigabit. And this is not Internet 2. This is just yet another regional educational network, and I know a lot of other states have regional educational networks. If you look at a map of educational networks in the U.S., you'll see there's East Coast schools have their own high bandwidth intra-school networks. And then of course, everyone's heard of Internet 2, which is a research network that at this point is so well connected to the internet. I mean, so many organizations that are connected to the internet too are also connected to the internet, that for all intents and purposes, it's really just the internet. And Internet 2 is mostly a 40 gigabit, in some places 100 gigabit backbone, some places only 10 gigabit backbone, and most organizations are connected to Internet 2 at 1 or 10 or 40 or 100 gigabits. And, there are a lot of organizations connected to Internet 2 that are not research organizations, or they're not schools. So, for example, almost all the national laboratories, whether it be Sandia National Laboratory or Lawrence Livermore or Lawrence Berkeley Labs, or even like CERN in CERN in Switzerland, the Large Hadron Collider. It has some high bandwidth connection to Internet 2, which allows them to distribute data to Fermilab and to UCSD and to a bunch of other schools. So when I draw the Internet cloud, what I really mean is this is the public networks that you have access to. It could be your commodity ISP. You may have multiple connections to commodity ISP links. You may have multiple research connections, Digital California, Internet 2, or some other initiative. You will typically have a gateway router. This is sort of your BGP presence to the rest of the world. Could be a Cisco device, could be a Juniper device. Most organizations have 2 of them at least, redundant, so they'll have links to Internet 2, and then sometimes they'll have links to each other. And then you'll have some set of distribution nodes, and usually if you have redundant internet routers, so we'll call it I gateways. Then you'll have some sort of backbone router. Or distribution router. So this is essentially your network border, the stuff that's closest to the rest of the world. So when somebody visits www.yourschool.edu, this is the presence that tells the rest of the world how to route to you, and then all your traffic is going to come over some links, and it's going to get dumped onto your network in some way. The internal core network, switch to a core that works. Your internal core network is, depending on how big you are and what your resources are, is typically going to be 2 or 4 or a ring of main node routers. Sometimes it's a ring where they're connected to each other like this. Sometimes they're cross-connected. It's not too important what the core of your network looks like. And then you'll have an edge distribution router. Call it edge dist. This may be like a Cisco 6500 or some other switch. And it will typically, I'm getting out of my camera's view here, so you will typically have edge switches. These might be Cisco 3550s, 3560s, 3750s, 4506s. It could be or it could be HP, or it could be some sort of commodity switch that has high density, lots of ports, 24, 48 some odd ports, and end user workstations would be plugged into these. So you have computers, and they're plugged in through the wall to these edge switches. And then, so if you just wanted to trace from the wall in this room Typically, that's connected to some patch panel that's connected to some edge switch. There's a whole bunch of edge switches for, like, say, this building. And all those edge switches pull back into a edge distribution switch. Edge distribution switch, your entire network might be switched, and this might be routed. Those terms probably don't really matter very much for this discussion. They're going to get dumped into the campus core at some point, and somehow they're going to get to one of these main backbone routers. This backbone router may actually just be one of these. It'll be connected to your edge routers. Usually one of them is going to be a failover, so you're only going to be using one anyways. And then that's going to get you on the internet. Now, if your school is highly distributed, so if you have like multiple sites, so if you have say a campus in California and a campus in Pennsylvania or something like that, then you would essentially replicate this 2 times. So this is going to be like per geographic site you would typically have this. And so the thing that would connect your 2 geographic sites would be the internet. And if you made your network look flat in some way, you'd be using IPsec or some sort of VPN tunnel technology over the internet. So this is the sort of typical network infrastructure for your entire campus. What gets kind of complicated is some schools separate out their ResNets and some don't. And it sort of depends on if you're IP rich or IP poor. So if ResNet has its own set of IP addresses, and you can look at a ResNet IP address and go, oh, that's ResNet as opposed to a campus address, you're probably separating out your ResNet program. Now, you may separate out your ResNet program into literally physically different network infrastructure. So you'd have ResNet edge switches, and you might have campus instructional and faculty and department edge switches. They'd be physically different switches. Possibly even physically different edge distribution routers. You may have, a physically separate network, or you may just logically separate them out. So you may, these switches typically have the ability to do what's called a VLAN, where VLAN is essentially the ability to say this switch is a virtual switch, and I'm going to group these 4 ports into this network, and these 4 ports into this network, and these 2 ports into a different network. And so as far as the workstations plugged into the switch are concerned, they're on different switches. So you might have like ResNet VLAN. So you have one shared resource switch, and you have a ResNet VLAN, and ResNet machines are plugged into that, or ResNet wireless access points are plugged into that. And then that VLAN gets trunked up in some way, and it gets kept separate at some point. And so you might have hanging off over here the ResNet router. Call it ResNet gateway. And so all the ResNet VLAN can get trunked. Call this the ResNet VLAN can get trunked to the ResNet gateway, and then get routed at this point back into the core. Really, the way you do it can be very variable. And so you're going to have to adapt what I'm saying and the ideas that I'm providing sort of to the architecture that you have. But for the most part, the architecture shouldn't be a huge hurdle. You should be able to get access to the resources. If your ResNet is not separated at all from the rest of your campus, then there's really almost no difference. So usually if you're like a really small school, and a staff port and a ResNet port are basically the exact same port and all the same IP addresses, everything like that, then you may not be able to do ResNet-specific network security. You might have to just do campus-wide network security. But usually you'd only have the 2 combined if you're a small school anyways, and so it's probably not that big a deal. So let's talk about the sorts of data sources that you could potentially have. So because your network has routers, these routers almost certainly can export NetFlow. Basically, all Cisco devices, or very close to all Cisco devices, can export NetFlow. And so, if you're not familiar with NetFlow, NetFlow is essentially like a telephone call record. So if machine A talks to machine B, whether A and B are on the same, both on campus or one's on the internet, like you go to Google or something like that. NetFlow is a record that says such and such IP address source, some client machine, on such and such protocol, TCP or UDP or IP, sent such and such amount of data, 10 packets, 30 bytes or 300 bytes or whatever, to some other destination IP address, destination protocol, well, the same protocol, destination port. So NetFlow So if you go to Google, www.google.com. So you're some client machine contacts google.com. So let's say your client machine is 1.2.3.4, and let's say Google is, let's pretend Google is 8.8.8.8, and let's just say you connected to them on the web. So then a NetFlow record would be something like 1234 and then some random ephemeral port, so 60,000. So you connected to Google on port 80, HTTP. So you connected to Google on port 80. So this, it's going to say TCP, and it's going to say something like you sent 30 packets and sent 64 KB of data. And then it's going to say Google sent, say, 10 packets and sent, let's say they sent a megabyte, 1 megabyte. And it's also going to have a start time and a duration. So it's essentially a call record. It doesn't tell you the data that was actually transferred. It just tells you a little bit about the data. So it's like, if I call so-and-so, then the phone company has some record that says my phone number called some other phone number at such and such time, and the call duration is this long. You get a little bit more information from NetFlow. You get the port, you get the protocol, you get the number of packets, you get the total amount of data. NetFlow is a pretty good source for doing forensics, figuring out what happened. It's good at tying other data sources together. It's not very good as a data source all by itself. The internet's full of IP addresses, and some IP addresses are both good and bad. You can have IP addresses that on one service, HTTP, they're perfectly fine, but if you talk to them on the IRC port, then that means that you're compromised. You can have hosting providers that like web hosting providers where they're running a whole bunch of websites out of one IP address. So they've got one bad customer who's running some malware command and control on their server, and they've got 100 good customers that aren't. And so if you're just looking at NetFlow, all you see is that you contacted such and such machine on port 80, and that may be .NET command and control, or it may be legitimate web usage. And also bad guys, they're able to change IPs all the time. There's things like Tor. They're pretty decent. They've got fastbox so that they can change the IP addresses that their domains are pointing at all the time. So it's pretty hard just using NetFlow to really do any really good network security. It's much better to tie additional, figure out what happened and tie other data sources together and sort of get a broader, more complete picture of what is happening on your network or what happened on your network. So that being said, you should export NetFlow and you should keep it because it's a pretty good resource. Exporting NetFlow, it doesn't really cost you anything. You have to have some machine to be able to receive it. But that can be, you can pretty much run any Linux machine you want, and you can use the open source OSU Flow Tools package, for example, for free, and it'll receive all the NetFlow and it'll store it in data files for you. It's not going to give you a good search interface. You'll be able to search through it manually, but it'll be there. So for free, you could get all the data and you can actually search the data. There are free web interfaces for OSU Flow Tools that allow you to search the search flows. There are other vendors have products. There's Landcope has a product that'll receive NetFlow and give you a good search interface for it. I think formerly Mazu, then now Riverbed has a NetFlow product. There's a bunch of other companies that have NetFlow products. Some of them are pretty expensive, and sort of in keeping with our theme of doing this on a shoestring budget, you could do it for free. And NetFlow. So the reason I mentioned NetFlow first is because you already have the existing network hardware to export NetFlow almost certainly do anyways. And you can get some value out of it, but you can't get a lot of value out of it. So if you don't export NetFlow, it's not the end of the world. There are some other data sources that you may have that you haven't necessarily thought of as data sources. So if you have a web proxy, like a reverse web proxy, where if a client on campus or a client on Resnet goes and browses the web, then they pass through like a content filter, such as there's WebSense, there's Cisco has the WSA, the Web Security Appliance Cisco iron port has the WSA. There's Blue Coat proxies. Most of them are designed to be content filters or like web security appliances where they'll block threats. But you don't necessarily, great if they're blocking threats, that's awesome. But you can use them as a really, really valuable data source because they're almost certainly collecting logs that say, so and such IP visited such and such URL, and here was the user agent string, this was the URL that they requested, here is the time, some information about the request that they made. And that can be an incredibly valuable data source because most malware comes via web exploits. So you can see the web activity that they were doing, you can see the web exploits in logs, and then when the malware gets loaded on their machine, the malware itself uses, typically, the most modern malware uses HTTP for its command and control mechanism. And so you'll see the malware command and control in your web proxy logs. And so whether you are searching them in real time, or if you're dumping them into some location, whether it's a log collecting utility like Splunk or some other log collection source, web proxy or reverse web proxy logs, whether it's CSA, Blue Coat, or whatever, can be an incredibly valuable source of information about what's going on your network and what malware you may or may not have. Now, if you don't have a web proxy, reverse proxy, and clients when they're doing http://www.google.com, if they're just going direct and they're not passing through anything, you can still collect that data, but it's going to require that you put some box on your network that's receiving it and actually storing logs. And so I'll talk a little bit about that, because a lot of the solutions that I'm going to discuss involve essentially you putting a machine on the network that's seeing traffic in some way. Another source of data is your DNS servers. Whenever you want to reach out to google.com, your machine has to do a lookup to find what IP address that is. Malware uses malicious domains. They don't typically hard code the IP addresses in the malware. And the reason they do that is because they want to be able to change IPs relatively frequently. They don't want you to be able to use your NetFlow or just block an IP address with an ACL or a firewall and stop it. They want it to look somewhat legitimate. They want it to look like a valid web request to some domain, so they pick just random names and they point them at some IPs they control, and they can change the IPs or the servers by just changing the DNS entries that the domain is pointing to. And so your DNS servers, basically every organization has recursive DNS servers for your clients. And you're probably using Bind, but you could be using Active Directory or something else. You can export those logs. So you can look at all of the recursive DNS requests that are being done by all of your clients. So let's pretend you have your DNS server here. You might even have like an Anycast setup where you have multiple DNS servers that all share one IP address, but you'd have to export the logs from all of the DNS servers. That can be, if you can identify malware command and control domains, that can be an incredibly valuable source. If this machine is looking at bad stuff, therefore it's compromised. You'd be surprised how good a data source this is, and you already have the infrastructure set up for it. All you have to do is turn on logging and export it somewhere. So you have to have you need to be able to turn on logging, and you need some machine to be able to receive these logs. So you can usually use like syslog. And then you just need some machine running syslog-ng or some other syslog collector, dump it out to text files, and you could just for a shoestring budget, you could just run a cron job that greps through for a list of known bad domains and alerts you. You could do that for free. And so the difficulty would be in identifying the malicious domains in the first place, but that's actually not as hard as it may sound. And you can also use public websites like malware domain list that has a long list of known malware domains. And you can load that in, and you can grep through, and you can find compromised clients that way. That's pretty successful. I personally think you should do all of what I described, but I understand that each organization is going to be able to do some things and not other things. There are also times where, DNS logs are not always used, and even if you exported logging on your DNS servers, that doesn't stop the malware from going and looking up to be like Google's public DNS, so like OpenDNS or Google's 8.8.8.8 public DNS or 8.8.4.4 public DNS. And so if you're only exporting logs on your DNS servers, you're not going to see clients that have manually configured their DNS resolution to be some other DNS resolver, or malware. There's a number of pieces of malware that just go and use Google's public DNS. There are solutions to that. You could capture all of the DNS packets on your network at one of your choke points, and you could log those. And that's an incredibly valuable source, because then there's no way to get around it. You don't even need to export logs on your DNS server, because you just get it right off the wire. And there's no way for the malware to hide in that. So if you can do that, that's really valuable. I'm working on a white paper about that, because Cisco's gone that route, and that's how Cisco's doing the DNS logging. It's working really well. And it's a shoestring budget. It's homegrown. We're not spending any money on any products to do that. And then, so let me talk about the stuff that you don't necessarily have the infrastructure set up right now. There's some schools have IDSs set up. It seems like most higher educations, most universities don't have IDSs set up. I know UCSD didn't have IDSs set up for a very, very long time, or they only did in just like the business and financial departments. They didn't really have IDSs set up for like the entire university. This is kind of surprising, because IDSs are such good, valuable sources of data. Now, so an IDS is an intrusion detection system. An IPS is an intrusion prevention system. If you listen to any of the network security marketing from the vendors that make them, whether they're Symantec or McAfee or whoever is going to be making the IDSs, or IPSs, they always emphasize like inline, auto-defending, prevent exploits, prevent. If your IDS can prevent, or IPS can prevent stuff, great, but you should look at your IPS as a data source, not necessarily as a real-time prevention source, because it's pretty trivial for an attacker to get by your IPS, or your IDS. So you want to look at those as just a sort of a tap into your network, so that you can search network traffic, so that you can define signatures that are going to tell you something bad is going on, and not rely on it as like your first line of defense. So one way to deploy IDSs, and this is not the shoestring budget way, but one way to deploy IDSs is like to put, if imagine this is your edge network, you put an IDS on essentially all of the links into your core network, or you put IDSs sort of at the edge, close to the clients, and you turn on full packet reassembly, full fragmentation reassembly, full everything mode on your IDS, and supposedly network security magic happens. That's the expensive way to do it. The really shoestring budget way to do it is to have one IDS for your entire organization, and it can be done. So if you can put an IDS around here, somewhere, typically if you have like one backbone router with almost all of your traffic going over it, and ignore the fact that if you have a failover link where you have a second backbone and you have a second gateway, but it's not in use, it's like for failover. If you're really on a shoestring budget, don't worry about doing a failover for your IDS. Just if all of the traffic normally, under normal conditions, passes through one link, just put the IDS there. And if you fail over because this goes down, then you're not collecting data anymore, but fix it and then get your traffic flowing back. And don't spend twice the money. We're talking about a really shoestring budget here. And you don't have to spend any money on the IDS. You just have to have some hardware that is capable of receiving data. So you can configure, since I know Cisco switch is the best, you can configure your switch to use a VACL. It's VACL. A VACL essentially allows you to create an access control list that that matches some traffic and copies it somewhere. So I think it's a VLAN ACL. But you could look at just port 80, TCP port 80 traffic, just HTTP with a VACL, and it says replicate to such and such a port, and then you could plug a Linux server into this port and receive a copy of all of the traffic that's going by on your backbone router, your gateway router, or some other network choke point, assuming you only have one. It's really cost effective if you only have one. I'm sort of assuming that you're a small school or that you're able to arrange all your traffic to go through one point. And then it's just a matter of, you have some Linux machines that gets a copy of all of your traffic. It's just a matter of installing Snort, which is a free IDS program, and configuring rules, or running TCP dump on the machine. If you set your VACL to do like UDP 53 and TCP 80, then you can capture all your UDP 53 with TCP dump to files, and you take a copy of all of your DNS traffic that's going by, and you could search through it later if you wanted to, using Wireshark or some custom written tool if you wanted to write one. Or you could, if you don't. So the benefit of having a machine on your network that's getting a copy of all of your traffic is that you can do anything you want, and you can basically do it for free as long as you have the machine. So you can use it's an open source program called Bro IDS. It's by a couple of researchers at Berkeley and I think Lawrence Berkeley Labs. Bro IDS it's designed to be like a research IDS, but it has some HTTP plugins that will reconstruct HTTP logs for you. So if you just send TCP port 80 traffic to this machine and you fire Bro IDS, and you give Bro IDS a copy of all the traffic, it will spit out HTTP logs telling you all of the HTTP activities happening on your network. So if you don't have a Blue Coat or WSA or WebSense or some sort of web proxy, you can still reconstruct all of your HTTP logs for free, assuming that you can spend the money on the hardware to do it. And you only need one machine. And so at UCSD, when I set this up a few years ago, there was one link, and it averaged about 6 gigabits of traffic a second. So we put a Dell 2U Linux machine in a rack, put a 10 gigabit fiber Ethernet card in it, configured a Cisco 6500 with a VACL just TCP port 80 traffic to replicate all the traffic over this fiber link to this machine. So this machine, it's got a 10 gigabit link. It typically saw around 6 gigabits of traffic. And we did all of our work. So we ran Snort on this box, and we wrote our own Snort rules. And we ran Bro IDS, and we reconstructed all of our HTTP logs. And we ran another program that I wrote that I'll talk about a little bit later. And we were able to do it all with one box. And so this one box cost us, it was like $3,000 for the server and like another $1,000 for the 10 gigabit Ethernet card. So it was like a $4,000 investment. It's a one-time investment. There's no support contract or any of that crap. All the software was free, or we wrote it ourselves. And we were able to find just an unbelievable amount of malware. We had no visibility into Resnet in terms of malware before that. And with this, we were finding, I don't know, Scott, I mean, how many, 30, 40, 50 infections a day sometimes?
I think the highest we got was like 87.
Yeah, I mean, it was a sort of the clouds parted and the sun shining through moment where we finally had visibility into what was going on in the network. And because, even though UCSD's Resnet network is sort of physically and logically separate from the rest of the campus network, we put it sort of at the campus level, so we were able to do the detection, the malware detection, for more than just the Resnet program. And I have a config file that I'm going to give you guys today. It's actually on a little CD image that you have as part of this lab. That has the sample Snort config that I worked on. And I'm going to talk a little bit about another program you could run here. But having a machine like this is going to give you sort of the ultimate visibility into your network. And any software that you want to run to sort through the packets on your network to figure out what's going on, find out what machines are compromised, this will do it. And you can reconstruct any logs that you're not getting anywhere else. And I think $4,000 sort of qualifies as a shoestring budget, considering you get such a big bang for your buck. Granted, you do need someone that knows how to do it and manage it and that sort of thing, but it's not really a full-time position. An existing security engineer can do it. And if you don't have an existing security engineer, you can get a smart student to do it. And I should emphasize that this is not even inline, so you don't have to worry about what happens if the box goes down, what happens if I screw up the config, and it's just getting a copy of the packets. Now, so has anyone ever seen the program called DriftNet? It's pretty popular at DEF CON. So DriftNet runs, it's designed for wireless networks, but it'll run on a regular network. But so you fire up your wireless card, you put it in promiscuous mode, assuming there's no wireless encryption or anything like that. What DriftNet does is it reconstructs all of the TCP streams that it sees going by, and it extracts images, all of the JPEGs and PNGs and GIF images out of the network traffic, and it displays them to you. So as people are surfing the web, you see the images go by and they go up on screen. And it's super popular at DEF CON and part of the Wall of Sheep, where they pull all the images off the wireless network and they show them to people. So it's not very useful. It's not much more than sort of a party gag, kind of a fun prank. So I wrote a program called XCAP. And it's sort of DriftNet for EXEs. It's open source, it's free. The source code is on Google Code. You can go and download it. It's release quality. And what XCAP does is, if you have a machine seeing a copy of all your network traffic, it extracts Windows executables out of the network traffic and it saves them for you. And so as your clients are going and browsing the web and getting exploited and downloading malware, or as the malware is running on their machine and it's going and grabbing updates to the malware, any executable that goes by on the wire that it's able to identify as an executable, it extracts a copy out and it saves a copy. And so as you're running it, you get more and more and more copies of executables, and that was the source of, well, it was an incredibly valuable source. So if we knew a machine got compromised, so the ultimate scenario is that you have some IDS signature, whether you wrote it yourself or you went and ran bleeding sorts or some other malware IDS signature, and you see such and such machine start firing an IDS signature. You go and look at the XCAP logs and you see that they downloaded a couple different executables all like 5 seconds before they started firing those signatures. You have a copy of the malware that was delivered on their machine. You can send that copy to VirusTotal. You can figure out what it is. You can send that copy to your antivirus vendor, McAfee, Symantec, Trend Micro, whoever it is. Maybe create signatures. You can call the user and say, hey, we just saw you were triggering Zeus such and such IDS signatures, and we have a copy of the malware, and it looks like it's the variant such and such. And VirusTotal says that Trend Micro detects it, but McAfee doesn't. So you might want to install a trial version of Trend Micro on your machine. Whatever. I also set up a malware lab. So the way it worked was I had a farm of machines that were running VMs, and I used an open source program called Cuckoo. C-U-C-K-O-O, I think is how it's spelled. It's called Cuckoo Box. And it's open source and it's been improved significantly since I last used it. But it allows you to manage a whole bunch of VMs. So you give Cuckoo a directory of executables, and it runs an executable on this VM, and a different executable on this VM, and a different one on this VM, and so on and so forth. Runs them for some set period of time, default 15 minutes, and gives you a packet capture and a list of all the files, a list of all the changes, and then it restores the machines, all the VMs back to original. And so I had XCAP running on our IDS machine, our do everything IDS machine, capturing executables, running them in Cuckoo, and then I come in, 10,000 executables every single day. I'd come in, I would just look through the network traffic for the ones that did, just basically a small number of the executables actually did any network traffic at all in 15 minutes. looked through the ones that were doing network traffic. Oh, that one's legit. That one's legit. Oh, that's bad. That's bad. That's bad. Figured out which ones do I already have an IDS signature for? Which ones do I need to write an IDS signature for? Which ones look like completely new variants? And so I was able to stay up to date and completely on top of the malware problem, or as close to on top of the malware problem as one could be, or one person could be, using programs that are either free or I wrote, or in just essentially one machine seeing all the network traffic on the network. And so almost all of the executables that you saw in the last lab or in this lab were all extracted off the network using XCAP. XCAP works really well for an organization where you only need to put one box because you have one network choke point. It would be really unfortunate if you have multiple gateways. So if you're like a big complex organization like Cisco, then you have this entire network sort of replicated like 100 times. And so there isn't one network choke point that you could possibly run a machine at. And so you sort of you've already replicated this infrastructure a whole bunch of times anyways. You'd have to replicate your security infrastructure too. And so this is one of the problems that big companies face that most schools don't face. And so XCAP needs work. It's not very good at, it's not aware of like other instances of XCAP running. They don't communicate with each other. You sort of have to manage, like if one sees an executable and this one sees the same executable, then you get two copies of it. It doesn't have a cluster mode. It doesn't stay in sync or anything like that. So that's work yet to be done. But XCAP can keep up at 6 gigabits, no problem. It doesn't really drop any packets, can continue to extract executables off the wire just fine. And if you configure snort right, you can also keep up at 6 gigs. You configure bro right, you can also keep up at 6 gigs. So you could do, and 6 gigabits is more than most schools have in terms of like continuous bandwidth anyways. So there's got to be one other, okay. If you don't have either the manpower or the resources or whatever, you don't have the inclination to do this, or if you don't have, say, the authority because you're not your school's security group, there are products, two of them come to mind. One is FireEye, and FireEye is essentially a box just like exactly what I'm describing. You put it on your network, you give it a copy of all your network traffic, it extracts Windows executables off the wire, it runs them in VMs, it does the network log processing. It essentially is one box that has a list of malware command and control domains and a list of known bad executables and known bad IP addresses. And it's sort of the commercial version of what I'm describing that you could do manually. So I have no idea what FireEye costs. It's probably expensive. But if you could afford FireEye and you didn't want to do it yourself, it seems like a pretty reasonable solution that would do a lot of this. You still have the problem of you have to get a copy of all your network traffic, and so that may be a big hurdle. And then there's another vendor, Damballa. It's out of a group of researchers out of Georgia Tech. And it sort of takes a similar idea to what I was describing, but it's based a little bit more on NetFlow. So you give it a copy of your traffic, I believe, and you also give it a copy of your NetFlow, and it looks for malicious patterns in traffic flows, and it has a list of bad domains and that sort of thing. I haven't done a side-by-side comparison like in depth, but it's been my experience, and I've overheard from a number of other folks that have both FireEye and Damballa running, that they're sort of complementary. Damballa finds stuff that FireEye doesn't, FireEye finds stuff that Damballa doesn't. It's also my understanding that FireEye is a little bit more comprehensive, that it's better at finding known command and control. But I think Damballa takes sort of a machine learning, computer science-y aspect to it, where it can find unknown stuff, and FireEye can't really find unknown stuff. FireEye is more of a signature-based system. So I think we're 15 minutes into this, so I better shut up and we better start working on the VMs. Does anyone have any questions or anything like that, or concerns, or reasons why this won't work, or any other ideas or data sources? Yes, sir.
Can some of those gateways, like for Resnet, can that be like a big firewall, big Cisco firewall with virtual LAN there?
You like a Cisco ASA or something like that?
Or where in that picture would you put a big firewall?
Well, so typically your firewall is just a device in line. It's not really a router. It's just a device in the path. A firewall can give you can do a pretty decent job of protecting your clients from active exploits, but a firewall basically can't do anything to prevent your clients from going out and getting themselves exploited. So UCSD Resnet has a pretty comprehensive firewall. I don't know what's happened to it in the last year and a half or so, since I haven't seen it in a year and a half, but it had a huge number of incoming ports blocked that are, ports that students would never be running as services. Or if they were running them as services, they really wouldn't want to expose those to the internet. And so, I mean, I've talked about a list of maybe like 60 some odd services. Things like the Dell Open Managed Services, if they were running like a Dell server, or oh shoot, I'm drawing a blank, but it was a long list of services that if a student were running this service, they really don't want to expose it to the world. For example, like the Windows services ports, 135, 139, 445, UDP 137. And then, some little bit shadier ports like PC Anywhere and RAdmin. I think RAdmin's like port 4899. And then there were ports that, like, some vendors, like a Toshiba laptop will have some help services port running on some fixed number, and you would block that. A bunch of stuff. We did leave things like remote desktop open, because students really want a remote desktop to their machines from home. And we left SSH open. So students, the few students that are running Linux or Mac with an SSH name, and they want to be able to access their machine remotely. So there were some services that we did leave open. That does not, no matter how comprehensive your firewall is, no matter if you block every incoming port, that does not stop. As long as your users can browse the web, they can get compromised. In fact, browsing the web is like 99% of your vectors at this point. This is not 2003, 2004, 2005 anymore. We're not dealing with Sasser, Blaster, Nachi, Welchia, Code Red, Sasser. We're not dealing with worms anymore. So, or God forbid, let's hope we're not dealing with them anymore. So the solution to dealing with worms was to segment your network as much as possible and then put firewalls in every segment and isolate, so keep stuff isolated as much as possible, sort of go into this sort of quarantine behavior where, you're showing symptoms, go over there and you can just keep the infected people infected and we'll keep you isolated from everyone else. And you did that via network firewalls. Network firewalls are great for protecting servers, and they're great for protecting services. They're really terrible for protecting clients. Your clients should not have any listening services. You can just block all incoming ports if you want. That's not going to stop them from getting compromised. Yes?
So any of these solutions, do they do real-time protection? Is it eventually something that can happen where?
So FireEye does do real-time protection.
How does it block any exe from being downloaded? Pop up a message?
Yeah. So there's a few limitations. So if you have the device in line, you could put this device in line. If you gave it 2 Ethernet cards and you Ethernet in, pass through the machine, Ethernet out, you could do inline, and you could run Snort inline or something, or you could run FireEye inline. If you run inline, you have to worry about, like, what happens when it fails? Does it fail open? That sort of thing. Is it a bottleneck? What is the latency add to the network? It adds some complication. If you don't do it inline, you could still potentially do some protection by forging TCP resets. So that is, this is like how the Great Firewall of China works. Basically, you're some client. Let's draw it over here. So you're some client, and here's some server. So C, S, and let's pretend that here's your connection. Ignore all the network devices it passes through. There's some tap. Some, call it Fire or some other device you built yourself, or Snort IDS or something like that. And it sees the bad traffic, and it is able to inject a TCP reset this way and a TCP reset that way, and tell the server and the client, it tells the client that the server reset it, and it tells the server that the client reset it. And it hopes that both the server and the client will kill the connection. That's some level of real-time protection. The problem with real-time protection is seriously overrated and seriously limited. With the device that I described here, where you've got some Linux machine that's seeing all your network traffic, you could do almost real-time detection. This is what UCSD has done. It's got some snort signatures to identify malware command and control. When that when that IDS-SIG fires and it says malware command and control, a little script picks it up, looks up the host, figures out what switch port is connected to, what is its MAC address, drops its MAC address in the MAC address table on the switch. Boom, they're off the network. Latency is like 30 seconds. So that's more or less real time. There are so many. Whenever you say real-time detection, you make so many people incredibly nervous. For all sorts of reasons, reliability reasons, oversight reasons, just technical limitations, just so many problems. Real time does not really buy you anything. Being able to detect it alone is probably way better than where you're at right now. So if you get the latency down to, if you get the latency down to 1 second, you're real time. If you get it down to 30 seconds, you're real time. If you get it down to 15 minutes, you're pretty close to real time. If you get it down to an hour, you might as well be real time.
Yeah.
If you're running a report 2 days later and going, oh, all these machines were compromised, and then blocking them out, you're not real time anymore. But you're still probably way better than you are right now. You can probably still beat the student into the door. So if you detect them, you run the report and you block them the next day, 24 hours later, you probably have already put them on a list and blocked them before they've come to you. So that alone is significantly better than probably where you're at today. Yes?
So those 40 or 50 so machines that you were detecting every day with the malware, that's what you were doing, blocking their internet access and letting them come to you to repair them, or how are you handling cleaning up their machines?
So I was working for UCSD's Central Network Security Office. We had a Resnet program of students and staff that would actually handle the support requests. Okay. And they essentially did what we covered in the morning session.
But so you sent, how did the student know that they were infected? Did you actually track them down and figure out what machine it was, what student owned it, and then contact them?
So for wireless, if it was a wireless machine, they got blocked and they got an email. So they got blocked and they got a page that says you're blocked and a description why. And if they were plugged into the wall, Resnet, not wireless, their MAC address would get dropped. And they would have no communication, but Resnet would get notified saying, we dropped such and such user because of this reason. And then Resnet, I believe, would turn around and email the student. And we would hope that via their iPhone or via their wireless connection or their dozen other computers that they would find out about it. Blocking is amazingly effective at getting the student to contact you. When you take away a student's internet, you might as well shock them. They're going to come and complain incredibly loudly and find out why and what happened. Actually, what mostly happened is that if they got blocked on wireless, they'd find out right away. And if they got blocked on Ethernet, they go, my Ethernet stopped working, I'm going to turn on wireless. Then they get blocked on wireless, and then they get the notice why. And so they get blocked twice, which made Resnet's job a little bit more of a headache because then they'd have to unblock people in 2 locations. But yeah. And if the biggest hurdle for you guys to do this is notifying the student, you don't have to block. If you can identify the student, you could send them an email and say, please stop doing this, or please turn off your machine and bring it in. The reality is that students are not going to do anything unless you force them. Well, that's true of everyone. I mean, you're not going to change your oil until your car's smoking, and you're not going to, you're going to put off your taxes until April 15th at 11:59 p.m. Everyone puts off everything as long as possible. It's sort of human nature. Blocking is very effective at getting people motivated. And maybe you have a reprieve during finals week where you don't automatically block during finals week or whatever. Any other questions? I think we're 30 minutes away from a break, but we should probably take a 5-minute break right now and get our Windows VMs started up. And I'm going to have everyone run malware in the VM, look at the network traffic, and then we will discuss based on the network traffic, what are the types of signatures you could write, and what are the types of data sources that you can use for identifying that malware. And then you can take that, if you have existing IDS deployments, you can turn those into existing ID signatures in existing IDSs. If you have existing web proxy logs, you can turn those into queries in web proxy logs. If you have DNS logs, if you already have some level of data sources, you can just leverage that in today. And if you don't have any data sources, you can think about how you want to build out some sort of infrastructure. And you can get an idea in your head of, well, I already gave you an idea of what the infrastructure you could build is. I also want to give you an idea of what the signatures would look like to detect this.